So what is our new idea? So we want to look at partitions in a different way. For that, there is a diagrammatic representation of a partition of an integer, which is called Farage diagram, okay, or Farage shape. Now this is also called Young's diagram. It's also called Young's diagram. In many books, you will see only Young's diagram, okay, because Young has done much more work and then made what's called. We will look into it in a future lectures. We will look at Young's table, Tableau. So we look at standard Young Tableau, non-standard Young Tableau, and weak Tableau. Many kind of things are there. We will look at some of these things later, but not at the moment. Okay, so we will look at what is called Farage shape or Young's diagram, and it is as follows. Suppose you are given a partition of, let's say, 10, right? So let's say a partition of 10 is mu is equal to 5, 3, 2, right? It's a partition of 10 into 3 parts. Now I can represent this partition as follows. So for every unit, I will put as in a unit square. Let's say I take a unit square, right? So the unit square represents 1, let's say. Now to represent 5, right, as part of the partition mu, I put 5 unit squares in a row left justified. Okay, so all of them will sit at the leftmost part. So there are 5 of them. So this corresponds to 5 in our partition. Then in the next row of the shape, right, in the diagram, I will put exactly 3 unit squares again left justified. Right? And since the last part in the integer partition is 2, I will put 2 squares at the end. So I have now 10 unit squares, all of them distributed like this. The first line contains 5, next line contains 3, next line contains 2, all left justified. So the area of this figure is now 10 unit squares, and that is why, we denote by, like we said that the area of mu is equal to, right, the number that it is partitioning, right? So if you are looking at Farage shape, for example, the number of unit squares defines the area, and therefore there is a reason, and that is the reason we call mu, the size of mu, as area of mu. Now, okay, so here is the here is the partition of, so the figure that partitions 10. Now let us look at partitions. There could be several partitions, so there could be several such figures, right? They will be distinct. So here are the partitions of 4, right? So Farage diagrams of partitions of 4. So what is the first partition? The first partition represents the partition 4. The second one represents the partition 3, 1. The third diagram represents the partition 2, 2. The fourth diagram represents the partition 2, 1, 1. Right? And the last diagram represents the partition 1, 1, 1, right? And these are precisely the 5 different partitions of 4. So they correspond to these figures, right? So the Farage diagram represents the partitions of numbers like this. Now, a formal definition of the Farage diagram can be given as follows. So FD of mu is the set of all I, j in n cross n, right? Such that 1 less than or equal to I less than or equal to k, and 1 less than or equal to j less than or equal to mu I. So this makes it left justified and top justified, right? So it's going to appear in the top left corner of whatever you are looking at. So the Farage diagram is going to be exactly like this. So this is something we already observed, that if a box has unit area, then the area of the Farage diagram of mu is the area of mu. which is the number that it is partitioning. Okay. Now here is another very interesting observation. So let us look at the partition of 21. Okay. So we are looking at partitions of 21. So here is a specific partition of 21 that I am giving, right? So the partition of 21 is as follows. It's 9, 6, 3, 2, 1. So there are 9 boxes in the first row, 6 boxes in the second row, 3 boxes in the third row, 2 boxes in the fourth row, and 1 box in the final row. Now, here is another partition of 21 again. But now here, so it's a partition, let's say mu dash, where the first row has exactly 5 boxes, second row has 4 elements, third row has 3, then 2, 2, 2, and 1, 1, 1. Right? Can you find a relation between these two figures? If you look at these two figures, you will notice that suppose you take the line, right? The line goes from the northwest corner to the southeast corner, right? That line, right? So 45 degree. And put that line on the diagonal, right? Like this. And then take the reflection of this onto both sides, right? The reflection with a mirror. You are going to precisely get the same figure that is on the right hand side. Okay. So I'm going to get the same figure on the right hand side. Okay. Okay. So just verify it yourself. These figures are in one-to-one correspondence with this reflection. So you take any figure here, do a reflection, you will get another figure here, and that figure will again be a partition of the same number that we are looking at. So I take this figure, take a reflection, I will get a partition here. Now can you see something else that is relating these two? Okay. So what relates these two is that in the first case, we had a partition of 21 into 5 parts. Now, when you take the reflection, this column becomes the row, first row here. So therefore, this is a partition where the largest part, because the top row is 5, because that is going to be the first row, right? So now we see that the bijection from that we were trying to prove, like P star of n comma k to, right, the set containing, the set that counts, that is counted by P star of nk to P of nk, right, is just a reflection technique in our diagram, right? So you take the reflection, you will get a partition, another partition, where the number of parts here becomes the largest part, and vice versa, right? The number of parts here becomes the largest part here. So what we have observed is that length of mu, right? The mu be the first partition is mu1 dash, right? The first element of mu dash. And similarly, and length of mu dash is equal to the first part of mu, right? Mu1, which is 9, right? So this is equal to 9. Okay, so this gives a pictorial proof that that P star of n comma k is equal to P of n comma k. Now, let us look at a couple of more things. We want to prove the recursion formula, right? So the recursion formula that we wrote for P and K can be proved using the Farage diagram again. So what is the proof? So here is the proof, right? So this picture represents the proof. So you have let us say the Farage diagram, right? And suppose the first column, right? I mean, first column is the largest column. That in the sense that there is some box, right? The last row, for example, is a singleton, right? So this guy is a singleton. So what I do, I just remove this guy from the picture, and I will get a picture here. Now, what is the property of this picture? This picture is a partition of n minus 1 because the area has reduced by 1 because I removed one unit cell. And the number of parts was reduced by 1 because I removed one row. And therefore, it's a partition of, this represents the partition of n minus 1 into k minus 1 blocks. Right? Now, if I have any partition here, I can just add one at the bottommost part of the first column, and I will get a partition here where the last row is a single cell, right? So therefore, there is a bijection. Similarly, if you have at least two elements in the last row, then therefore two columns are full columns. So what I can do is that I can remove the entire first column from this, right? Then I will get a Farage diagram here where the number of rows are the same because I have only removed the first column, but the second column is also full. So it's a partition of n minus k because I have removed exactly. So there are k rows here. I have removed exactly k cells, and I get n minus k cells here remaining. So it's a partition of n minus k into exactly k blocks, right? So that is the proof of the recursion. And these two are disjoint because these figures does not have this thing here, and they are disjoint, and therefore we can add them. Okay, so here is another homework question for you. So consider a rectangular grid with let's say A columns and B rows. Okay, so here is the grid where you have column number 1, column number 2, etc., column number A, and row number 1 to B. Okay, so take a rectangular grid with A columns and B rows. Now, what we are looking at previously was Farage diagrams. Now, Farage diagrams are left and top justified. So, let us see how many such Farage diagrams can sit inside this box that we are looking at, right? So, here is the grid shaped box, and in this box, we want to see how many Farage diagrams can be put inside. Right? They fit completely inside. So can you count the number of such Farage diagrams that sit inside this box of size A cross B, right? So this is a homework, and try to find a proof by finding a bijection to some set that you already know how to count.